Okay, let's do some problems for Chapter 11. So in Chapter 11 we have two topics. One is simple harmonic motion and the other is waves. Okay, so first problem, in a physics lab you have a 0.2 kilogram air track glider on the end of a spring of negligible mass. It started oscillating. The time from when the glider moves first through the equilibrium point to the second time it moves through that point is 2.6 seconds. Find the period and the spring constant. Alright, so we got to think about what's going on. So we've got a object that's going between plus and minus the amplitude. Okay, and we're told that the time it takes to go from here and then back the next time it goes through is 2.6 seconds. So that is actually 1/2 of the cycle. A full cycle would be to plus A, back through 0 to minus A, and then back to the center. Okay, so the period is going to be twice 2.60. So that's 5.20 seconds. All right. Now we want to find the spring constant. So what do we know about a mass on a spring? We know the period is 2 pi root m over k. I know the period. I know my mass. I want to find the spring constant. So to get the spring constant out, I'm going to have to square both sides. I'm going to square both sides. It's going to give me t squared is equal to 4 pi squared m over k. So that means k is equal to 4 pi squared m over the period squared. Okay, so put in my numbers. 4 pi squared, my mass is 0.200 kilograms. The period is 5.20 seconds. I'm going to square that. And I get my spring constant. Spring constant is 0.292 newtons per meter. Okay, so period 5.20 seconds, spring constant 0.292 newtons per meter. Alright, second problem, we want to look at these two waves and from the picture figure out what's the amplitude and what's the period. Okay, so for wave A, which is this wave here, it goes up and down between these two values. We need to look at where does it go up and down to. It looks like it goes between plus 2.5 and minus 2.5. So I'd say for A, the amplitude is 2.5 meters. And for B, going across, looks like it's something like 3.5 meters. All right. Now we want to look at the period. The period is the time that it takes to go from where it started back to exactly the same point in the cycle again. So here it starts at 0 and goes up. So here I'm going to start at 0 and going down, so I'm not back at the same place. So I go all the way here, and so that's 4 seconds. So for A, the period is 4.0 seconds. For B, now I start at my peak. I'm going to find out when is the next time I'm at my peak and going down. So be right up here, and that's 2.0 seconds. So for B, the period is 2.0 seconds. Okay, so you've got to look at the picture, find the place where it's going through exactly the same point in the cycle again. The third problem, we're going to use conservation of energy to solve. We've got 0.5 kilograms, so mass is 0.500. Glider attached to the end of an ideal spring with force constant K equal to 450 newtons per meter. Undergoes simple harmonic motion with an amplitude of 0.040 meters. Okay. I want to compute the maximum speed of the glider. The speed of the glider when it's at x is negative 0.015 meters, the maximum acceleration of the glider, and the total mechanical energy of the glider. Okay, so we're going to have to use conservation of energy. So our total energy is at either end where the kinetic energy is 0. We've got the energy is 1/2 Ka squared, just the potential energy stored in the spring. And that's also equal to, at the equilibrium point where the potential energy is 0, 1/2 mv max squared. And at any given point, it's equal to 1/2 mv squared plus 1/2 kx squared. Okay, so what am I going to do for the first part? I want to find V max. So what I'm going to do is I know K, and I know A, and I know M, so I can just set these two equal to each other and solve for V max. So For A, I've got 1/2 Ka squared is equal to 1/2 mv max squared. And this just looks like something that we did back in chapter 6, right? So V max is equal to Ka squared over m square root. So that's 450 times A is 0.040 squared, 4 centimeters, divided by a mass of 0.5 square root, and I get my maximum speed is 1.20 meters per second. Next thing, we want to find the speed of the glider when it's at a position of negative 0.015 meters. So now what we have to do is we have to use this part of the equation. So we say 1/2 mv squared plus 1/2 kx squared is equal to, and we can set equal to either one of these. So let's set equal to 1/2 Ka squared. And I want to solve for v. So first thing I can say, okay, hang on, I got a half everywhere. I can get rid of that. So I've got mv squared is equal to Ka squared minus kx squared. So v squared is equal to Ka squared minus kx squared over m. And so v is equal to the square root of Ka squared minus kx squared over m. And actually, you might remember in class we had an equation that we derived if you want to memorize it for it, but otherwise it's easy enough to solve for this. So let's put in our numbers. So we've got square root of K is 450 times the amplitude, 0.040 squared, minus K times the position that it's at, and we want to solve it for when x is negative 0.015, so we do negative 0.015 squared, over the mass, which is 0.50 kilograms. And sorry, I should put 450 in there for K. And put that in your calculator. And we get V is equal to 8.35 meters per second. Now be careful when you're doing this. Remember, the square of a negative number is a positive number, so you're not going to have a negative and a negative making a positive. All right, part C, what's the maximum acceleration of the glider? If you look at the equations we had, we said that A max was equal to omega squared times the amplitude, and omega is root K over m, so it's K over m times A, so 450 times 0.040 divided by the mass, 0.5, and we get 36, and the units for acceleration are meters per second squared. All right, last part, what's the total mechanical energy? Well, total mechanical energy is the energy here, or the energy here, or the energy here, kinetic plus potential. So let's just do our first one again, 1/2 Ka squared. So it's 1/2 times 450 times 0.040 squared, 450. And we get 0.36, 0, and the units are joules. Okay, so we're just using conservation of energy to find the different things in the problem. The next topic in the chapter was talking about simple pendulums. So a simple pendulum is just a mass on a string, and here we're told we've got a mass of 2.35 kilograms, and the length of the string is 1.50 meters. We want to know how many swings per second will these fixtures make. So how many swings per second is the frequency. All right, so what do we know? We know the period is 2 pi root L over G. We know L. Mass doesn't even come into it. So it's 2 pi times the square root of 1.5 over 9.8. Gives us the period. So 2.46 seconds is the period. So the frequency is 1 over the period, or 0.407, and the unit is hertz. Okay, so pretty simple. All right, now we're going to talk about waves in a string. So waves in a string, we've got two equations that we need to worry about. One is that the speed of a wave is equal to its wavelength times its frequency. We're told we've got a frequency of 40 hertz and a wavelength of 0.75, 3/4 of a meter. So we can use that to get the speed. And the other thing that we know is that the speed of a wave on a string is equal to the square root of the tension divided by the mass per unit length. Okay, so we've got the mass, we've got the length, and we want to find the tension. All right, so first of all, let's find V. V is equal to lambda F. So 40 times 0.75 gives us 30 meters per second is our speed. So we've got the speed, we've got the mass, we've got the length, we want to find the tension. So let's square this whole equation to get rid of that square root. So I got V squared is equal to Ft divided by m over L. So Ft is equal to V squared times m over L. So that's 30 squared times the mass, 0.12 kilograms, divided by the length, 2.50 meters, is 43.2, and the unit is newtons. Okay, so a problem like this, or a problem where you're given the tension and asked to find the speed or the frequency or the wavelength, are all possibilities. So it's all working with these two equations in conjunction. Okay, problem 6, talking about intensity. So we've got sound with intensity of 10 watts per square meter at a distance of 30 meters away. We want our intensity to be 1 microwatt, so 1 times 10 to the minus 6 watts per square meter. And we want to know what's our new distance. So let's call these I1 and R1, I2 and R2. Okay, so what do we know? Well, we know that the intensity is equal to the power over 4 pi r squared. Okay, so since I know I1 and R1, I can find what the power is. And the power from the jet plane doesn't matter where you are. That's produced by the engine. So the power is I1 times 4 pi R1 squared. So that's 4 pi times 10 squared, times 10 times 30 squared. And we get 113,097.24 watts is the power of the engine. Alright, so now I've got the power. So now I've got I2 is equal to the power over 4 pi R2 squared. I know the power, I know P, I want to find R2, so let's rearrange it. 4 pi R2 squared is equal to the power over I2. So R2 is equal to the square root of the power over 4 pi I2. And now just put in our numbers. So 113,097.24 over 4 pi times 1 times 10 to the minus 6 square root. And we get 94,868.3 meters. And so that's really far. That's 95 kilometers, or around 60 miles away. Okay, so it's a huge difference in distance that you have to be. Okay, last problem. I've got a steel wire with a tension of 800 newtons. I know the mass, I know the length. So that tells me I can get my V. My V is equal to root of tension divided by mass over length. So I know all those things. I want to know what's the frequency of its fundamental mode of vibration, and what's the highest harmonic that can be heard by a person who can hear frequencies up to 10,000 hertz. So first of all, let's find V, since we know we're going to need that. So V is equal to tension, 800, divided by the mass, 3 grams. I'm going to put that in kilograms, divided by 0.4 meters. And I get my speed is 326.6 meters per second. Alright, so now standing waves, what's the fundamental frequency? Well, our equation is that the frequency of the nth harmonic is equal to n times v over twice the length. So I want the fundamental, so I want n equals 1. So the frequency is V, 326.6 meters per second. So 1 times V over twice the length, and I get 408.25 hertz. In part B, what I want to know is I want to know what n is given a frequency. So I'm given that the frequency is 10,000, and that's equal to n times V over 2L. I want to know what's n. And I'm going to have to round down to the nearest integer, because this may not work out to be an integer. So I've got 10,000 times 2L over V is equal to n. So 10,000 times 2 times 0.4 meters over V, 326.6 meters per second. And we get n is 24.49. Okay, but n has to be an integer. If I round it up to 25, then we're going to get a frequency higher than 10,000, so the person won't be able to hear it. So I've got to round it down, and so n equals 24. The 24th harmonic is the highest frequency that the person could hear.